So you asked, how many times are we going to see a graph where we've got time and concentration on the X and the Y axis? Well, a few more. If I have a reaction where reactant goes to form two products, over time, reactant concentration is going to decrease, and over time, product concentration is going to increase. This downward slope is not as fast, not as steep as this upward slope because of that coefficient. Okay, cool. We want to develop formulas for determining how reactant changes over time, or even how product changes over time. And we're going to do that so that we can calculate how much reactant remains after a certain amount of time, or how much product forms after a certain amount of time. How long will it take to get rid of 90% of the initial reactant? So 10% of the initial reactant remains, but 90% has reacted. We're going to come up with formulas for calculating these things. One quick reminder, way back at the beginning of the semester, we said the rate of the reaction could be defined as negative delta R delta T, losing reactant concentration over time, or negative 1/2, positive 1/2 delta P delta T. We're going to take advantage of that assumption in one moment that the rate of the reaction could be defined as the rate of consumption of reactants over time. We're going to use that. Let's talk about some graphs first. This first plot, this first rate law, that's what that is a second order reaction. So over time, the concentration of the reactant is going to decrease pretty steep. This is a pretty downward sloping, pretty dramatic shift downward, right? Right. What about for a first order reaction? It will be exponential like the second order, as in it's curvy, not a line with a straight slope. It's a curvy downward also, but it's not as downward as this one is, as steep. Maybe you're following along. Hold on. What about for a zero order? Often called a zeroth order. I know, that's a little bit crazy. A zeroth order is a straight line with a negative slope over time. Sorry, I should have written time on the axis before I started drawing. And this is reactant concentration as a function of time. So the zero order reaction, we could measure that relatively easily, but we need exponential equations in order to calculate how second and first order change over time. We don't love exponential equations, so if we can do a little manipulation, we can change these equations to be linear instead of exponential. What? Hold on. Let's start with first order. First order is one of the most common reaction types that we will see, so we're going to start there. So if we take advantage of the rate of the reaction could be defined as negative delta R delta T, and set that equal to the rate law, raised to the first power. Why would we do that? Again, we're trying to develop formulas, equations, for how the concentration of a reactant changes over time. So if I rearrange this equation to put K delta T on one side and delta R over R on the other side, if I integrate this equation, don't lose me, don't let me lose you. Integrate this equation from 0 times 0 to time t. This integrated equation simplifies to the ln of r at time t minus the ln of r at time 0 is equal to negative kt. Maybe you don't remember calculus, maybe you haven't ever taken calculus, but I'm telling you where these equations come from just because I think it's helpful for some students to know where they come from, and it helps some students keep track of which equations are for which ordered reaction. Hold on. Keep up. Hold on. So this equation is called the concentration time equation, and it is only valid for a first order reaction. We started by integrating the rate law for a first order reaction. It's often written in this way, but it is sometimes written this way. ln of r at time t is equal to negative kt plus ln of r at time 0, also known as the initial reactant concentration. The reason it's written in that way many times is because that has the form of y equals mx plus b. And if I plot ln of r versus t, I get a line that has the slope of negative k. Bear with me. We're going to keep on moving to second order reactions and lather, rinse, and repeat what we just did for a second order reaction. I know it's second order. Oh, it's supposed to be purple. I know it's second order, so I'm going to take advantage of, again, delta R, delta T is the rate of the reaction, K, R squared. I'm going to rearrange to gather my R terms on the left. That's delta R over R squared equals negative K delta T. And once again, I integrate from 0 times 0 to time t. When I integrate an R squared kind of thing, that makes it 1 over R at time t minus 1 over R at time 0 equals positive kt. I can distribute my negative. That's what I actually did. Distributed my negative over to this other side. You may not remember integral things and how this works, but yeah. This is known as the concentration time equation for a second order reaction. Sometimes these are also called the integrated rate laws. Wonder why they might call them the integrated rate laws. Because I started with a rate law and I integrated it to get me here. It's often written in this formula, in this way that's in the square down there. But it is sometimes written this way, where it's 1 over RT equals positive KT plus 1 over R0. Why would we do that? Because if we do that, it's written in a Y equals MX plus B way. And if I plot 1 over R as a function of time versus time, I get an equation, I get a line with the slope of positive K. Bear with me. We got one more. Lather, rinse, and repeat, but this time for a 0 order reaction. It's a 0 order. I'm going to start with negative delta R delta T equals K times R 0. I'm going to rearrange to make it delta R over, this was supposed to be raised to the 0, sorry, that was supposed to be raised to the 0, over R raised to the 0, anything raised to the 0 is 1, negative KT, and I integrate from 0 to time t. Maybe you don't remember integrals, maybe you never had calculus, but if I integrate from 0 to time t and simplify, R at time t minus R at time 0, concentration at time 0, negative KT. Okay. This is known, you guessed it, as the concentration time equation for a 0 order reaction, also known as the integrated rate law. It is frequently found in the squared version there. It is often also found in this version. Why would we do that? Oh boy. That's because, yikes. That's because y equals mx plus b. If you plot concentration versus time, you get a line with a slope of negative k. Okay, what do I do with this information? The integrated rate law for a first order reaction was ln of r at time t equals negative kt plus ln of r at time 0. The second order integrated rate law was 1 over r at time t equals positive kt plus 1 over r at time 0. And the zero order reaction integrated rate law was r at time t equals negative kt plus r at time 0. So why do we draw these integrated rate laws? Why do we concern ourselves with these integrated rate laws? Well, frequently, in order to determine the order of a reaction, you can plot ln versus t, 1 over versus t, and concentration versus t, and see which one gives you a straight line. If concentration versus t gives you a straight line, it's a zero order. If 1 over versus t gives you a straight line, it's a second order. I almost said the wrong thing. Second order. If it's an ln versus time that gives you a straight line, it's a first order reaction. See what I mean? Concentration versus time, straight line. This is a zero order. When it's zero order, ln versus time does not give you a straight line. 1 over does not give you a straight line. It only gives you a straight line when it's zero order and it's concentration versus time. It only gives you a straight line for a first order when it's ln on the y-axis. It only gives you a straight line when it's 1 over for second order. 1 over concentration for second order. Negative k slope, positive k slope. That's what our concentration time equations tell me. Okay, now that we've done all of our calculus for the day, what else do we need to know about kinetics and rate law things? The rest of the world views first order reactions somewhat frequently, but they talk about the half-life of first order reactions. The half-life is the length of time required for a reaction to proceed halfway. So if you start at 0.1 molar concentration, how long does it take to reach half of that initial quantity? So 0.1 molar, half of that means 0.05 molar. How long does it take to reach that? For this particular reaction, that's 100 seconds. If I'm at 0.5, how long does it take to reach half of that value? That's 0.025. So that's 0.025. Oh, look, it's an additional 100 seconds. How long does it take to go from 0.025 to 0.0125? Oh, look, it's an additional 100 seconds. The reaction proceeds to give you the same half-life no matter how much time has elapsed. When it's a first-order reaction, the half-life is the same regardless. So this reaction is a 100-second half-life no matter what. First order, yeah. If I know the rate constant for the reaction is this value, and I compare this pink trace to a black trace, well, the black trace starts at 0.1. It takes less time to get to 0.05. It takes only that much time, so 50 seconds. It's got a shorter half-life. If we compare the rate of the pink reaction to the rate of the black reaction has a shorter half-life, which means it has a faster rate. The longer the half-life, the slower the rate. The shorter the half-life, the faster the rate. So if I compare the black and the pink to this new blue trace, this started at 0.1. How long does it take to get to 0.05? It takes 200 seconds to get to 0.05 and another 200 to get to 0.025. Actually, it doesn't even quite reach down there, but it should. That's just bad drawing on my part. I apologize. So it takes 200 seconds for the blue line, 50 seconds for the black line, and 100 seconds for the pink line to be consumed by half. If the pink line has a rate constant of 0.0069, the black line will have a larger rate constant, Shorter half-lives means faster rates. Faster rates means you need a faster rate constant, a larger rate constant. We're almost done. The half-life of N2O5 is 22.7 minutes, and it decomposes with a rate constant of this. What do we do with that? Number one thing that I should have said in video number 1, the units of your rate constant are important. And the units of the rate constant change depending on what the reaction order is. The units of seconds to the -1 or time to the -1 is indicative of a first order reaction, always and forever. And sometimes that's the only hint that you get that this is a first order reaction. So the half-life of this thing is 22.7 minutes with this rate constant. What do we do with this? For a first order reaction, the half-life can be calculated by 0.0693 divided by K. That will tell you how long the half-life is. But if you put 5.1 times 10 to the -4 into this equation, you're going to get 22.7 minutes. You'll have the unit conversion to get you from seconds to minutes, though. But since we were told K and half-life, what are we wanting to calculate? Well, there's a question back here. My PowerPoint is not cooperating, but there's a formula that will allow you to determine how many half-lives have passed. And we are trying to answer the question, this is what I was trying to get to, if 0.2 of the original concentration remains, how many half-lives have passed? This is where I was going. So, if 0.2 of the original compound remains, so using this formula down here, that means that number is 0.2. 1/2 / 0.5 raised to the n power means number of half-lives. 0.2 of the original concentration remains. Another way to say that maybe is 20% of the original concentration remains. These concentration time equations are often a percentage thing. If 80% of the original concentration has been consumed, that means 20% remains. If 20% remains, we're going to plug in 20%. But if they say 80% has been consumed, plug in 20%. You'll see what I mean as we keep working. So how do I solve for n? Anytime you have an exponent, you can solve that with logarithms or natural logarithms. ln of 0.2 equals ln of 1/2, and the reason I do that is because I can pull n out front as a coefficient in my ln. So ln of 0.2 divided by ln of 0.5, that's 1/2, right, equals n. Solve for n equals 2.3. 2.3 half-lives have passed. 2.3 is back there behind the green. All right. We will talk more about concentration time stuff. We will do lots of concentration time stuff. Goodbye.